questions? Things are good? All ready for Friday's quiz? Sure, why not, right? Remember again, Friday's quiz is just over the trig functions of angles, right? So we talked about doing trig functions of acute angles and then trig functions of any angle at all using the reference triangles. Okay, so shouldn't be a huge surprise what types of problems are on there, because I just want to know, do you know how the trig functions are defined, and can you use reference triangles to get values? Okay, so not a huge long quiz by any stretch of the imagination, just do you know those exact values? Okay. All right. So let's move on then and talk about getting graphs of the trig functions. So pretty much, this is pretty standard in math. You come across a new type of function, you want to get a picture of what it looks like. Right? So the picture helps with visualizing different properties of the function. And then the different properties, of course, that we might want to talk about for that particular function is, what are we allowed to plug in? What possible values can we get out? Where does it cross the axes? Those kinds of things, right? So those are the kind of things that we're going to look at today. And then as well as moving forward, talking about, well, starting with these standard graphs of sine, cosine, and so on, how can we transform them into other things that look like sines and cosines, but aren't just that base graph. So doing transformations of the graphs. Okay, so that's what we're going to concentrate on this particular section. But to do that, let's just get base graph down first. Well, if you don't have an idea of what the graph looks like to start with, you should start with the tried and true plug and chug idea, right? Pick some values for x, get some values out for y, play connect the dots, see what happens. Right? Okay. So let's do that for our purposes here. Let's just pick some values for x and get some values out for sine of x. We're going to do the sine function first. Now, usually when you're doing graphs, you might say, oh, I'll pick in like -3, -2, -1, 0, 1, 2, 3, and so on, right? We're going to be a little bit more smarter about it because we don't know necessarily what sine of 1 is or sine of 2 is, but we do know things like sine of pi over 6, sine of 2 pi over 3, those kinds of things, right? So we'll start with the angles that we know, and then see if we can get a rough sketch of what we want, what the graph has to look like. So I'm going to just start with the angles that would be in the first quadrant. Let's do 0, pi over 6, pi over 4, pi over 3, pi over 2. Start there. What are the values when you start at 0 and go up to pi over 2 for sine? Sine of 0 is 0. Pi over 6 is 1/2. Pi over 4 is root 2 over 2. Pi over 3 is root 3 over 2. And pi over 2 is 1, right? So if we're going to plot these on, let's just plot these points quickly just to see what we have. We would have the point 0, 0. Pi over 6 is 1/3 of the way to pi over 2. So if I go about 1/3 of the way over, I'd go up to 1/2. Pi over 4 is 1/2 of the way over. I go to root 2 over 2, which is about 0.7. Pi over 3 is 2/3 of the way over, and we're at root 3 over 2, which is about 0.866. And then pi over 2, we're at 1. So this is probably a little bit higher. It's okay. Oh, I erased it. That was interesting. All right. Anyway, we have this, so far, this general shape. So far, so good? All right, so what if we go kind of the next set of angles that would be in quadrant 2? The next set of angles that we would know the exact values of. So say, just scooch this over a little bit. 2 pi over 3. That's the next one over. 3 pi over 4, 5 pi over 6, and pi. Let's talk just a second about how I know where those are. What those are, I should say. If you think about going around in a circle, if you will, so just off to the side here, pi over 3 is here. That's a third of pi, right? Then there would be 2/3 of pi there, and then pi would be 3/3, right? Likewise, if you do the pi over 4 here, well, then 2 pi over 4 is pi over 2. Because 2/4 is the same thing as a half, right? So then 3 pi over 4 is the one that's here. And then for your pi over 6, 5 pi over 6 is just short of pi, right? Because pi would be 6 pi over 6, so it's just short. Okay. In other words, where those came from. Okay. In any event, let's see if we can figure out these values. Well, 2 pi over 3, 3 pi over 4, 5 pi over 6 are all over here in quadrant 2. Is the sign positive or negative over in quadrant 2? Positive, right? So the values that we get out are going to be positive. Looking at these three, what are the reference angles here? What's the reference angle for that one? Pi over 3, pi over 4, pi over 6, right? So these are going to have the same values as what their reference angles are, right? So we'll have root 3 over 2, root 2 over 2, and 1/2 for those three. They'll be positive because it's in quadrant 2. The reference angles are given, right? Remember when we have those nice angles that we know the exact values of, the reference angles are just ignore the coefficient on the pi, right? What about the last one? Well, pi is on the terminal side would be on your negative x-axis. Sine is up and down. We didn't go up and down at all, so sine of pi is going to be 0. Yep. So now if we put these points on here, 2 pi over 3 is 1/3 of the way over. We're here. 3 pi over 4 is half the way. 5 pi over 6 is 1/3 away from pi. And then we're back down at 0 again. So notice that for the sine function, you go up, and you come back down to pi to there, right? So far, so good? Okay. Well, let's see if we can get a little bit more. Perhaps go a little bit more quickly. All right, let's go over to quadrant 3. Let's think about what angles are in quadrant 3. Well, they're all going to have a pi over 6, pi over 4, pi over 3 in them, right? Well, here's, again, to here is 6 pi over 6, so a little bit more is 7 pi over 6. For your pi over 4s, you would have 1, 2, 3, 0, 1, 2, 3, 4 pi over 4, 5 pi over 4 is the next one. For your pi over 3s, you would have 1, 2, 3, 4 pi over 3. And then 3 pi over 2 is the one that's down this way. So what quadrant are we talking about? 3. So is sign going to be positive or negative? Negative. So all of these are going to be negative, right? Because they're all below the x-axis, right? Okay. Reference angle is pi over 6, so we get negative 1/2. Reference angle is pi over 4, so we get negative root 2 over 2, negative root 3 over 3. What's the last one going to be? Well, if you're at 3 pi over 2, you're on the y-axis, the negative y-axis. So what's the sign of that going to be? Well, if pi over 2, it was positive 1, so 3 pi over 2 is going to be negative 1. You can just use the same reference angle idea. So notice now, do the same kind of graphing here. Got a negative 1/2, negative root 2 over 2, negative root 3 over 2, and negative 1. We get that piece. Well, just kind of like by pattern recognition, what do you think is going to happen with the dots next time? They're going to go back up again, right? Okay. Let's verify that that really does work. The next set of angles you would have would be 5 pi over 3, 7 pi over 4, 11 pi over 6, and 2 pi. Again, if we just think about counting them, here's 1, 2, 3, 4, 5 pi over 3. 1, 2, 3, 4, 5, 6, 7 pi over 4. 2 pi, and the last one I didn't think about this way. 2 pi all the way around is 12 pi over 6, so it's just 1 short. That's the 11 pi over 6. We're in quadrant 4, so all those values will be negative. We have our reference angles again, so we'll get negative root 3 over 2, negative root 2 over 2, or 1 over root 2 if you prefer, and negative 1/2. By the time we get back to 2 pi, we're on the x-axis again. So what's the sign going to be? 0 again. So we really do come back up again. So if I draw this, and again, when we try to draw it, we try to make it smooth, right? We don't want to make it all jaggedy. We go up, come back down, go down, come back up. This gives us a piece of the sine function. We haven't done the whole thing yet, but it gives us a piece of it. Is it okay so far? Before we keep talking about getting these graphs, we'll go a little bit faster when we start going through the other ones. But notice that we've got a wave, right? It goes up, and it goes down, it goes back up. And it'll keep doing that actually over and over and over again. So sine functions, cosine functions are good for modeling things that repeat themselves. So if you do anything with electronics, for example, or any waves in it, see sines and cosines just as an example. Tides, anything that repeats itself, sines and cosines are pretty good models for them. So one of the reasons why we study trig function ideas. All right. How can we get the rest of the graph? We know we can plug in anything we want for x and get out sine of x. How do we get the rest of the graph? Well, notice once you've gone all the way around to here, once we've gone all the way around to here, I get coterminal angles, don't I? So the values will be the same. So when I go up, down, and back up again, and now I'm at coterminal angles, this would just keep going and repeat itself again from 2 pi to 4 pi. It would also repeat itself over here, up, down, and back up again here, right? It's just going to keep repeating itself because you're doing coterminal angles. So in this, and again, this is going to keep going up and then down again. This will go this way and back up again. It'll just keep doing this over and over and over again. It'll just bounce over and over and over again. So we refer to this type of function as a periodic function. In this case, it repeats every 2 pi. And the reason why it repeats every 2 pi is because 2 pi is all the way around the circle. Okay. All right. So let's see. Well, we'll collect some information about these, I think, on a different. Trying to remember how I. Yeah. Okay. We'll collect different types of information on this in a minute. But let's see if we can get cosine and see if we can find some similarities and some differences between the sines and the cosine graphs. Okay. All right. So let's do the next page, and then we'll come back and look at them together. same idea for cosine. Let's just start plugging in some values, but rather than me putting the table next to the side of it, let's just see if we can go and figure these things out. So I'll do a few of them. I will do a table for a few of them, but not write all of them out like we did for the sine function. Oops. Cosine. Again, let's start with 0, pi over 6, pi over 4, pi over 3, pi over 2. Start there. Remember, for sine, we went 0, a half, root 2 over 2, root 3 over 2, and 1. For cosine, what does it do? The opposite, right? It starts at 1, root 3 over 2, root 2 over 2, 1 half, 0, right? Goes the other way. We talked about that the other day. So if I plot these points, we would have something that looks like this, roughly. Not great, but we're just trying to get a sketch, right? We're not trying for perfection. If you want to try for perfection, go take an art class. If you want to really look good, just use a graphic device. As opposed to trying to do it by hand. Okay. All right. Notice that these were the angles that were in quadrant 1, right? We're going from 0 to pi over 2, we're in quadrant 1. When we go from pi over 2 to pi, what quadrant are we in? 2, right? Cosine is positive or negative in quadrant 2? Negative, right? So we're going to have a graph that goes below the x-axis then here, right? And it'll end up at, we'll have what? Negative a half, negative root 2 over 2, negative root 3 over 2, and negative 1, right? It repeats those same values, they'll just all be negative again, right? Just like what we did for sine. Okay. From pi to 3 pi over 2, what quadrant are we in? 3, right? Cosine positive or negative in quadrant 3? Negative. So we'll come back up again. Same values, we'll just come back up again. And then finally, 3 pi over 2 to 2 pi is in quadrant 4. So we'll go back up again and top out at 1. And so we'll get a graph that looks like, wow, I missed my points. I missed those two. Yeah, well, again, not looking for perfection, looking for the idea. We get that repeating idea, but again, once we get to 2 pi, it's going to repeat itself again, right? Same idea. We'll go through the same exact values again. So you're going to get another picture over here that looks exactly the same. And it'll keep doing this over and over again. So cosine's also going to go up and down all the time. Just like the sine function did. Okay? So the graphs are identical, they're just shifted, right? If you take the sine graph and move it pi over 2 to the left, you get the cosine graph. They literally are the same graph, they're just shifted off each other. Okay. All right. So let's see if we can collect some information. So that's what's on the next page. Are there any numbers that you cannot plug into the function? Do you see any holes in the graph? Any issues with plugging anything in? No. So what would you say the domain is? That's going to be the other one. If we're looking for the x's. Yeah, it could be negative infinity to infinity. It'll be all real numbers, exactly. So for both, the domain is negative infinity to infinity. Okay, so they both have the same domain. Range, we're going to look for the y's. How far up and how far down does it go? Negative 1 to 1, right? The smallest value you can get out is negative 1. The biggest value you can get out is 1. And you can actually get those numbers out, right? You can get out 1 and you can get out negative 1. So we'll use brackets on that for our interval notation. So negative 1 to 1. Let's do the last blank because the next few blanks will have to have one or the other kind of thing. The period. How long does it take for the graph to repeat? What interval do you need for the graph to repeat? 2 pi, right? Once we go any 2 pi interval length, it'll start repeating again, right? So both have a period of 2 pi. So again, these are similarities for the signs of the sine and cosine function. They both have a domain of minus infinity to infinity. Both have a range of negative 1 to 1. Both have a period of 2 pi. Right? Now, they do cross the axes in different places, right? Where does the sine function cross the y-axis? That's across the x-axis. I thought they say x-axis. I meant y-axis. Yeah. So if I go back over up here, where's it cross the y-axis at? It's here, right? At the origin, right? So the y-intercept here is going to be, for sine, it's the origin, right? What about for cosine? At 1, yeah. So the y-intercept will be 0, 1. And those are, I know we got some interval notation stuff going on. These are ordered pairs. Crosses the y-axis of the point 0, 0, crosses the y-axis of the point 0, 1. Okay. All right, what about the x-intercepts? Where does it cross the x-axis for sine?
At pi.
Yeah, it crosses at pi, where else? 2 pi, where else? 4 pi, where else? 0, where else? Yeah, negative pi, negative 2 pi, negative 3 pi, negative 4 pi, right? All the multiples of pi, correct? The way that we typically write that is we take a number times pi comma 0. So if you see an n times something, it means that we can do any integer here. By integer, we mean something that doesn't have a fractional part. So the integers are 1, 2, 3, 4, 5, and so on. Negative 1, negative 2, negative 3, and so on, and 0. Those are the integers. No decimal part. Right. Any integral multiple of pi gives you an x-intercept. What about for cosine? Where does it cross the x-axis? Pi over 2, where else? 3 pi over 2, 5 pi over 2, 7 pi over 2, negative pi over 2, negative 3 pi over 2, negative 5 pi over 2, and so on. Notice that they're all pi apart, right? If I scroll back up to my graph, this is a length of pi, right? This is a length of pi. This is a length of pi. Right? So the way we can express all the x-intercepts is we can do pi over 2 plus multiples of pi. And that will give us all of our x-intercepts for cosine. So again, domain, range, period, they all have the exact same domain of the range and period. The intercepts change, though, depending on which one you're talking about. Questions on that? Okay. So what we're going to do now is talk about how we can transform sine and cosine into other graphs. Okay? So starting with your sine or cosine as a base graph, we're going to do stretches and shrinks and shifts. For trig functions, they have special names. Okay? Looking at this one, I have y equals 3 times sine of x. If sine is my function, is that 3 on the inside of the function or on the outside of the function? Outside, right? If a number is multiplied on the outside of the function, does it affect the input or the output? If it's on the outside, it affects the output, right? So it's going to do something to the y's, correct? What happens when you multiply on the outside by a number? What happens to the y's? What happens to your graph? It stretches it, right? It makes it 3. In this case, it's going to make it 3 times as tall. Because it multiplied by a 3, right? On the outside, it affects the outputs. On the inside, it affects the inputs. So this is going to make it 3 times as tall. This number on the outside, let's go back up to the range. Notice that the range here goes from -1 to 1. What's the range going to be on this one? -3 to 3, right? Okay. We agree? So it's going to change the range from -1 to 1 to -3 to 3. It'll make it 3 times as tall. Okay? So the word we use when we multiply on the outside and talking about what happens to the y's is this amplitude idea. Okay? That's what the amplitude means. It's going to be, as a definition, it's, if you think about your original graph, I like to think about the x-axis as a baseline. How far up and how far down does the sine and the cosine go from the baseline? 1, right? 1 unit, right? It goes 1 unit up, 1 unit down, 1 unit up, 1 unit down, right? The amplitude is that how far you move from the baseline, okay? Not the entire length of the range, it's half the length of the range. It's how far do you displace from the middle, okay? All right? So for the original graphs, the amplitude is 1. For this one, we would say that the amplitude is 3. And in particular, your amplitude is half the length of the range. All right. So when we graph this, we'll start with our base graph. Ooh, that was bad. Start with your base graph. Well, try to get my base graph in here. That way. That's what your y equals sine of x looks like. When we say it's y equals 3 times sine of x, it's going to make it 3 times as tall. Yes? Oh, okay. Yeah, you're fine. Yeah. If that happens, just go. You don't have to tell me. It's okay. All right. So what happens with the 3 on the top when we multiply on the outside? We said it affects all the y's, right? Does this point change? Does this one change at all? No, that one doesn't change. Where does this one end up at? Here. 3. It goes up to 3, right? It was at 1. It's going to go up to 3. Does this one change? This one here? No. This one's going to go down to -3. This one will stay at 0. This will go to +3. -3, 0, 3, 0, and so on. So you'll get something that looks like that red graph instead. Why did it erase everything? Is there an undo on here? There we go. I don't know why it erased it. All right, so the red graph here would be your final graph. So this would be your y equals 3 sine of x. You've done transformations of graphs in other classes, right? You've done it in college algebra class or algebra 2 or whatever class you might have called it. Wherever you've taken it before. Okay. You've done, it's the same idea, we're just doing it for trig functions. It's nothing new. Doing it for trig functions and giving it a different name. Okay? Nothing terribly exciting. Is that okay? Okay. What's going to happen with this one in your next example? It makes it, it's going to shrink it vertically, right? We'll multiply everything by a half. So again, if we start with our cosine graph, which starts up at that y-intercept of 1, goes up, goes down, goes back. I notice I changed the scale on this one. I'm not looking for perfection. I just want to know that you have the general idea, right? For your new graph, we're just going to make it half as tall, right? Because we have a 1/2 on the outside again. Agree? Okay. So we'll go through the point 0 1/2 instead of 0 1. We'll go down to the point pi negative 1/2. But we'll still cross the x-axis in the same place. It's going to be half as tall as the others. What would you say the amplitude is on this new graph? What was the original amplitude? The original amplitude is 1, right? We multiply everything by a half, so now the amplitude is a half. Yeah. The amplitude is just going to be the absolute value of that number in front. It's always half of the range. The amplitude is always half the range. The range here goes from negative 1/2 to 1/2. So the amplitude's a half. Okay. So the amplitude of either y equals a times sine of x or a times cosine of x is, we have to be a little bit careful. We don't want to just say a. It needs to be absolute value of a. Your amplitude is always a positive number. When I put a negative sign in front of something, what does that tell you to do with a graph? When I multiply by a negative sign, what does it tell you to do? Flip it up to the x-axis, right? Flip it upside down. Does that change? If you flip it upside down, does that change the range at all? No. So I don't want the negative in there at all to describe the amplitude. So we want to do the absolute value of this. When the amplitude is that, it tells us that the range is negative a to a. Again, both of these have a baseline of the x-axis, so it means it goes up to a and down to negative a, whatever that a happens to be. And I should put absolute value bars around that because a could be negative. Just to make sure I'm hyper technical about it. The bottom number on that needs to be a negative number, and the top number needs to be a positive number. So if a is negative, I need to make it positive. So put absolute values on it. I've mentioned this before, but we can also find the amplitude from a graph by doing what? Well, the amplitude on a graph is half the range, right? So you can find the amplitude by doing the highest y minus the lowest y and divide it by 2. The amplitude is half of the length of the range. So take the highest y value on the graph, take the lowest y value on the graph, subtract them. That's the length of the range. We want half of it. That gives you the amplitude. Pardon me. So looking at that first example there, it asks, what's the amplitude in the range of 12 times sine of x? What would you tell me? What's the amplitude? 12. And the range will be negative 12 to 12. Good. For the next example, the amplitude is yeah. So do we care about the negative for the amplitude? Nope. So it's just 4/3. And then your range will be what? Good. Yep. Negative 4/3 to 4/3. Yep. Questions on that at all? All right, so this is just one shift, right? This is one shift, one transformation, and it was a vertical shift. So let's talk about another transformation. Let's do the vertical stretch or shrink. Let's talk about horizontal stretches and shrinks. Well, notice when the number was on the on the outside, it affected the output. Where's this 3 now? It's on the inside, right? So that affects the inputs, right? Agreed? So this is what's going to do a horizontal stretch or shrink. And remember, when it's on the inside, it basically does the opposite of what you think it should, right? When we multiplied on the outside by 3, it made it 3 times as tall. Does multiplying by the inside by 3 make it 3 times as wide? No, it does the opposite. It smashes it in, right? It makes it 3 times faster, if you will. Okay. I personally like to think of the number on the inside as a speed factor. This will trace out your original sine function 3 times as fast. It'll repeat 3 times as fast. So instead of taking 2 pi to repeat, it'll repeat every 2 pi over 3. Okay. So let's see if we can handle that. I'm sure we can. For your sine function, do I start at 0, 0, or do I start at 0, 1 when I start graphing? 0, 0. Good. So yeah, I'll go up and down and down and back up. So, and then do the same thing on the other side. Something like that. That's okay? That's what the original graph looks like. I need to make this draw 3 times as fast. Do not draw this next piece, by the way. I'm going to draw it, but I'm going to erase it after I'm done. So don't draw it. Or don't open then. I want a different color. There we go. All right. So if I do this 3 times as fast, from 0 to pi over 2, I need to draw in 3 periods. Okay? So you would have something that looks like it would go up. Gotta do it quickly. I gotta go up and down and back up. All right, and then I gotta do it again and then do it again. All right, I gotta do it 3 times in the 2 pi interval. That's the hard way to do it. Basically, what this number does right here is it changes the x scale. It divides all your x's by 3. So the easy way to do this, rather than redrawing, is change the scale on your graph. Instead of 2 pi here, where this is 2 pi, now it's red, of course. Where it's 2 pi, instead of 2 pi, that last number should be 2 pi over 3. Divide it by divide it by 3, multiply by a third. So instead of pi here in the middle, what should it be? Pi over 3. Here, divide this by 3, I get pi over 6. Divide that by pi over 3, I get pi over 2. That'll be 5 pi over 6. Negative pi over 6. Negative pi over 3. Negative pi over 2. Negative 2 pi over 3. There, I graphed it. That's much faster than redrawing it, isn't it? I just divided everything by 3 because that's what the 3 on the inside tells me to do. So in this case, the period now, it started at 2 pi and we divided it by 3. So this number here on the inside is what we're dividing by. Let's see if we can do the same thing for, I was going to redraw it, but I decided to do it the other way. I thought that was what the extra set of axes is there. But again, if I were to redraw it on this scale, I would have to draw it in 3 times. Right? It's going to be 3 times as fast. You can see, hopefully, if you're thinking about it from an application perspective, why we might care about changing the period. If you're trying to model something, for example, if you're modeling something that happens every year, like temperature, you want your period to be 12 if it's going to be months, or change your period to 365 if it's going to be days, right? You don't have 2 pi days in a year, right? So you don't want to change the period, okay? If you are thinking about modeling musical notes, those are waves, sound waves, right? The closer the waves get together, the higher the pitch, right? So you'd be changing the period again. So you can understand why we might want to be changing that period idea. Let's see if we can do the same thing for cosine. Again, I've got 2 sets of graphs there, but really I'm only going to draw one, because I'm not going to redraw it. Original cosine graph. Do I start at 0, 0, or do I start at 0, 1? 0, 1, right? So it starts up here, goes down, goes up, comes back down. Likewise does the same thing on the other side. So again, this number on the inside changes the period. Okay? It either speeds the graph up or it slows the graph down, depending on whether you're stretching it or compressing it. Okay? When you find the period, the period of the original cosine, is 2 pi. The number on the inside is pi over 4. So you divide the period by that number. If we simplify, the pi's will cancel, but the 4 is going to come back up to the top. So we'll get 8. Right? So instead of repeating every 2 pi, this will repeat every 8. All right? Well, notice that this is not very convenient to change this, especially if you put it on the same set of axes. 2 pi is about 6.3, 2.28 and change, right? It's not very convenient to move that to an 8 and then try to smash everything in there. It's going to look really crowded, right? So do the same trick that I just did a minute ago. Instead of 2 pi, which is the original period, what should the 2 pi become now? 8. Half of 8 is 4. Half of 4 is 2. And so this will be 6. So you have -2, -4, -6, -8. And now you have a graph. We change the scale. In fact, if you were doing this problem, you probably wouldn't have put the scale on first, right? You know what the cosine graph looks like. You probably would have said, oh, hey, the period is 8, so I'll make the cosine repeat at 8 and then fill in the numbers in between. A quarter, a half, 3/4, 1, essentially of it, right? That's half of 8, that's half of 4, halfway in between is 6. That's how I got the scale to begin with. Does that make sense? Okay. All right. So let's see if we can summarize this. When you're finding the period of y equals sine of bx or cosine of bx, well, again, the original period is 2 pi. And then much like what we did for the amplitude, if there's a negative, you'll divide by the absolute value of b. Usually we don't have to worry about that. There's properties of the sine and cosine function where we don't have to worry about the negative. We'll talk about that later. So let's do those quick 2 examples there at the end, and then we'll come back to this again on Friday. Looking at that y equals -3 sine of pi x, what's the amplitude going to be? 3, right? It's the absolute value of that number. Right? The absolute value of the number in front. How do we find the period? What will we do? Good. Divide 2 pi by pi and get 2. For the second one, amplitude will be 2/3. Good. The period, how do we find the period? Good. Divide by 1/2 and we'll get 4 pi. Is that okay? Not too bad? Okay. We'll do more of these next time, including doing some shifting, which we refer to for trig functions, refer to that as phase shifts. We'll talk about that, and then we'll do the vertical shifts at the end, and then we'll probably talk about some other trig functions before we take our quiz on Friday. So don't forget, quiz on Friday over 6.2 and 6.3. Otherwise, have a good one. We'll see you on Friday.